when you have an m by n matrix A, you'll remember that we defined the null space of A to be the set of all vectors in r to the n or c to the n or whatever. Let's say r to the n for now. So x in r to the n such that Ax equals 0, the 0 vector. And we know that this is a subspace of r to the n. So it's of interest to us to say, what is the dimension of that subspace? How can we find a basis for that subspace? And we do know something about how we might get started with this, because we know that if R is a matrix which you can get to by doing row operations to A and which is in row reduced echelon form, then you know that the solutions to Ax equals 0 are the same as the solution to Rx equals 0. So this is the same as the null space of R, where R can be reached by doing row ops to A. So in particular, R could be a row reduced echelon form matrix, and we know something about how to read off the solutions to Rx equals the 0 vector when R is in row reduced echelon form, because we learned about fundamental solutions. Now, in fact, what is true is that the fundamental solutions are a basis for n of R and hence for n of A, because those two things are equal. We're not quite going to prove this in this video, but what we are going to prove is that those fundamental solutions are linearly independent, so that only spanning remains, which we're going to do by a trick later on. The way I want to prove these things are linearly independent is by introducing this thing called the easy linear independence criterion, which is an easy way to prove that certain vectors are linearly independent. And in fact, it works much more generally, so not just for vectors like this, but for not just for column vectors, but for row vectors or for matrices or anything like this. But for simplicity, because it's the case that we need, I'm just going to state this for column vectors. So the criteria says, suppose you've got some column vectors, v1, v2 up to vk, and they have the property that for each I, there is a non-zero entry in a row of vi where all the other v's have got a 0 entry. And then the conclusion to that is that these v's must be linearly independent. So to explain what's going on here, let's just look at an example. You can find the full proof in the notes as usual, but we'll just look at exactly why this is true. So let's say we took v1 to be this thing here, so 2, 0, 5, 0, and v2 was going to be 0, 6, 5, 0, and v3 is going to be the vector 1, 7, 0, 0. Now there is an entry in v1 which is non-zero in a position where all of the other vectors have 0. And there is also an entry in v2, so this one here, in a position where all the other vectors have a 0. And there is also an entry in v3, so this one here, in a position where all the others have a 0. So these things fulfill the easy linear independence criterion. And it's actually very easy to see why this results in them being linearly independent, because what you can do is you can take a linear combination of v1, v2 and v3 equal to the 0 vector, and then just look at those special coloured in coordinates in that vector to deduce that the coefficients in the linear combination must be 0. So let's do this. So in this example, suppose that, let's say, a times v1 plus b times v2 plus c times v3 is equal to the 0 vector, the height 4, 0 vector. Then, well, shall we work it out? On the right hand side I've got 0, 0, 0, 0. What do I have on the left? Well, I'm actually only going to think about some of the entries on the left. So look at the yellow entry, the bottom entry of those vectors. I will have 2a here, and then I'll get b times 0 and c times 0. So I just get 2a in the bottom here. So before we do anything else, let's just think what this bottom entry is going to tell us. The bottom entry is then going to tell us that a is equal to 0, because 2 times a was equal to 0. So next, let's look at the third entry. So looking at the third entry of this linear combination, I got a times 0 plus b times 5 plus c times 0. So I'll just get 5 times b. Okay, so then again, just looking at this third entry, what does it lead to? 5 times b is 0, so b is equal to 0. Now if we look at the top entry, so in that top entry, I've got 0 times a, 0 times b, 1 times c. So I immediately get from that c is equal to 0. Okay, all three conditions, all three coefficients were equal to 0, so putting these together, v1 and v2 and v3 are linearly independent. So we show that if you've got a linear combination of those three vectors equal to the 0 vector, then a and b and c, the coefficients in that linear combination, have to be 0. So these things are linearly independent. And you'll notice we didn't even have to bother working out what goes there. Some horrible mess goes there. It doesn't matter because we have already shown that the three coefficients in our linear combination are equal to 0. So that's the easy linear independence criterion. Let's now recap what these fundamental solutions to a row-reduced echelon form system of linear equations look like. So we'll take a row-reduced echelon form matrix R, and we'll let the ij entry of R be A subscript ij, and we'll let this be m by n, and suppose that it has leading entries in rows 1, 2, 3 up to R. What we then did when we defined our fundamental solutions was to say that each of these columns either has a leading entry or doesn't have a leading entry. So we'll let the ci's be the numbers of the columns which have leading entries. So C1 is the number of the column containing the row 1 leading entry, and C2 is the number of the column that contains the row 2 leading entry, and so on. And the other columns which don't have a leading entry, we'll call the numbers of those columns D1 and D2 and D3 up to, say, DK. And then we were able to write down the fundamental solutions for this matrix equation. So if you think back to what was going on here, these columns with no leading entry corresponded to free variables. Free variables meant that you could choose their value freely in a solution. So you could get your fundamental solution, which came from setting one free variable to be equal to 1 and all the other free variables to be equal to 0. And it turned out that what that gave you for your jth fundamental solution, obtained by putting the jth free variable equal to 1 and the rest equal to 0, it had this expression just here. So we called our jth fundamental solution Sj, and it had this slightly nasty looking summation expression. But actually you can write this in a slightly easier way, so it's perhaps easier to think just what does this column vector look like. It is a height n column vector, because column vector should have the same number of rows as R had columns. R had n columns, and they were all either labelled by a C or by a D. And if you think what goes into these columns, well, for example, wherever column C1 would be, that would have the entry minus A1 dj. And column C2, wherever that is, that would have the entry minus A2 dj. So that's what the columns labelled by C's would look like. On the other hand, in column dj, you will get a 1 because of this part here of the fundamental solution. And in the other columns, so in the columns dj prime, where j prime is not equal to j, you would just get a 0. So those, in the rows labelled by dj. So that's what this solution would look like. All of the entries in this solution are either labelled by a C or by a D, and if they're Ci, then you get the entry minus AI dj, and if it's labelled by dj, then you get 1, and if it's dj prime, you get a 0. So let's look at this in an example. This is kind of hard to follow without actually thinking very carefully about an example. So let's look at the example down here, where R is this 3 by 5 matrix here. So here we have M is equal to 3 and N is equal to 5. So we should have a certain number of fundamental solutions, and those fundamental solutions will be height 5 column vectors. So what have we got? M is 3, N is 5. There are leading entries in rows 1 and 2. So R is equal to 2. So if we look at these columns, so there are columns labeled by numbers 1, 2, 3, 4, 5. There are 5 columns. And if we think about the C's are supposed to be, well, C1 is supposed to be the number of the column with the row 1 leading entry. So here is C1 is equal to 2. And C2 is supposed to be the number of the column of the row 2 leading entry. The row 2 leading entry is right here. So the number C2 is equal to 4. That's the column of the row 2 leading entry. And the D's were the numbers of the columns with no leading entry. So we've got D1 here is equal to 1, and D2 here is equal to 3, and D3 here is equal to 5. So that's what's going on in these, in this particular matrix. And then the fundamental solutions, there will be one fundamental solution for each of my free variables. So for each of these numbers, D1, D2, D3. So for S1, what we will get is, well, let's think what happens. We should have a column vector of height 5, 1, 2, 3, 4, 5, like this. And if we label the columns, so there's a column, so if we label the rows D1, C1, D2, C2, and D3 like this. And the first fundamental solution, we put D1 is equal to 1 and the other is equal to 0. And then the C's should be minus the corresponding entries in that column. But all the entries in the column right here are 0. So what we have there is zeros. Okay, so let's put these things in green. So there is our first fundamental solution. Let's do the next one. So the next one might be a bit more interesting. So S2, again, S2 should be a height 5 column vector. So its rows are labeled by D1, D2, D3, and C1 and C2. And this is the fundamental solution corresponding to the second free variable. So we put that one equal to 1 and the others equal to 0. And then let's try a different color here. C1 should be minus the entry in row 1. So we would have a minus 2 here, and C2 will be minus the entry in row 2 of the column just here. So that will be a 0. So here we would have a 0. Okay, so that's our second fundamental solution, and the final fundamental solution, S3. So this time we should have D1 and D2 equal to 0 and D3 is equal to 1, and then we would have again minus the other entries in that column as our entries in the rows labeled by 3, so we would have a minus 3 here and a minus 4 there. And that is our final fundamental solution in this example. That's how we constructed our fundamental solutions. And let's look and notice that at least in this example, these fundamental solutions actually follow the simple, they fit into the simple linear independence criterion. Because if you look at the rows labeled by a D, well, the D1 row would have a non-zero entry 1 for the first fundamental solution, and then the other fundamental solutions, that variable was set to 0. So you'd have a 0 here and a 0 here. And then if you look at the D2 row, so the D2 row is going to be 1 here and 0 in the other fundamental solutions. And if you look at the D3 row, then that would be a 1 here and a 0 in the other fundamental solutions. So the fundamental solutions are going to fit into the simple linear independence criteria using the rows D1, D2, T3 up to Tk as the places where there is a non-zero entry in one of the vectors and 0 entries in all of the others. So the proof of this is then simply to apply the simple linear independence criterion. So proof, apply the easy linear independence criterion. So the jth fundamental solution has a 1 at entry, so row dj, and all the other fundamental solutions So let's say Sj prime, where j prime is not j, are 0 in row D j. So these fundamental solutions fit into our easy linear independence criterion, and therefore they really are linearly independent. So what we've shown then is that our fundamental solutions are linearly independent. They are linearly independent elements of the null space of the matrix R. We'd like to also show that they are a spanning sequence, but what we're going to do is deduce this from something that we learn later on. So for now, we're just going to stop there.